So welcome everybody. I wanted to give a seminar now when this new book of mine has been released, especially here in Oulu, because it's been in Oulu where this has happened. Oulu's been one of the first areas where this embedded IP technology, so using the internet in very small devices, wirelessly, over low power, Bluetooth, over all kinds of low power radios. Oulu has been the birthplace of this technology. So I think it's appropriate that we have the first seminar on this new book here in Oulu. So thanks everybody for coming. The title of this book is called 6LoWPAN, the Wireless Embedded Internet. And the reason we called it the Wireless Embedded Internet is exactly for part of the reasons that Heikki pointed out, that we're really talking about up to 1 trillion new small devices joining the internet. And most of that will happen through wireless technology. So we're really talking about a whole new internet, which probably is going to be larger than the internet itself someday. So it's a really interesting area, both for business and for research as well. This is a book I wrote with a colleague of mine from IETF standardization, Professor Carsten Bormann, who's from Universität Bremen. So he's a German professor. So I have a lot of thanks for Carsten for being an excellent co-author. And Carsten is co-chair of 6LoWPAN standardization. So Carsten is one of the people who leads the standardization process for these protocols in the IETF. And this is really the world's first book on this subject. So it's really an interesting to be along with writing something that's never existed before. So we've done a lot of work to try to explain something that's totally new and that we don't have references for anywhere. So a lot of these things we've had to explain for the first time. So it was quite an interesting process to make that happen. So I hope that this is understandable for everybody. Part of the purpose of the book, though, is not just to be a book that engineers buy and read, but to be something that people can use for teaching. Because as many of you know, this is a new technology. We need to teach students how to use this. We need to teach engineers in industry how to apply this in their products. We need to teach really a whole new industry about low power IPv6. So in addition to this book, we actually have a website where we're releasing course material and free exercises about the book. So we actually have 120 slides, which is a free course that I'll be releasing today. This afternoon I'll release those slides. Some of the slides you'll see now, I don't have 120 slides luckily, so you won't be here for like 4 hours. I only have 100 slides. And so you can download those and use those in your own courses. You can send them to friends. They're under a Creative Commons license even, so you can even dissect the slides and reuse them. Everything's good. So please take a look at the website as well, if it's helpful. So the idea here is to give everybody a little bit of background into what this industry is, what this low power IPv6 is and why it's important. What's the Internet of Things and how does this new technology fit into the Internet of Things? And then they give a really light overview of the book and the technology. I don't want to go into the nitty details of every bit and byte. I don't think it's useful for most of you. You can look at the book and all the exciting standards for that. But I want to talk about how the technology works and why it's important and where you can use it. I think this is the most interesting thing for all of you. So I promise not to keep you here for much longer than 2:30. We try to even stop a little bit after 2:30, so there's time to finish the rest of the puulla before you leave. So we'll talk about the Internet of Things, but we'll also talk a little bit about the Internet itself, because to really understand how embedded IP works, we need to understand how the Internet works. And not only the Internet, but the newest generation. So that's IPv6. So I'll explain what IPv6 is and why it's different from the Internet that we're using mostly today. I'll give a really light introduction into 6LoWPAN technology, so what it is and how it works. We'll talk a little bit about link layer technology. So what are the types of links you can use this? So low power Bluetooth, 802.15.4, so Zigbee radios, narrowband radios, even power line communications. So how can you use this with different links? We'll talk about commissioning these networks and maintaining them. A little bit about the importance of security. What kind of security options do we have? This is probably one of the most important factors in commercial networks is security. Mobility and routing. So what are the routing technologies that are being applied to this domain? They're a little bit different than what's been applied to ad hoc networks before, so it's quite interesting. And finally, we'll talk a little bit about application protocols, which is one of my favorite subjects these days. And those of you that know me, you can interrupt me anytime, because that's how that's how I like to talk. So if anybody has a question, just raise their hand and I can answer. So what is this Internet of Things, and how does this fit here? I think Heikki gave a really good introduction to what we were thinking a decade ago when we started working on this trillions of embedded devices. And what he said was very true, because the way the Internet is structured today is that we really have a core Internet consisting of approximately 1 million nodes, and these are the servers. This is the infrastructure that keeps the Internet up and running. Big switches, routers, and servers. It's about 1 million nodes. It doesn't change very fast. It increases in capacity, but it's pretty stable. On top of that, we have what's called the fringe Internet. And the fringe Internet is what's been growing so far today, and that's today in the billions of nodes. And the growth of the fringe Internet is totally related to the number of users of the Internet. So this is really people-centric. This is growing as fast as we have people with mobile phones and PCs, some home entertainment, multimedia equipment. So that's the fringe of the Internet. That's never going to get bigger than some billions of nodes, because those devices require people to use them and maintain them. But now what we see happening is that we have all kinds of applications being connected to the Internet which have nothing to do with the number of people which have them or buy them or maintain them. These are totally embedded applications. So things like smart metering. This is one of the most important things for us at SensiNode, for example. The energy industry is really interesting for this type of technology. Industrial automation, another very important one. I'll talk about a standard called ISO 100. ISO 100 is the new standard for industrial automation with low power IPv6. Logistics and different kinds of asset management, also really, really interesting. So tracking things and tracking people in factories, warehouses, hospitals. Transportation, so keeping track of goods and vehicles in transportation is another very hot topic. RFID and access control, this is something we'll talk about with one example. Phones. And not the phones itself, because for me a phone is in the fringe Internet, but the things connected to phones, which is what Heikki pointed out that we looked at 10 years ago together with Nokia, is that when are all these sensors going to be started to be connected through phones to the Internet? And that's starting to happen today. You have the new Nokia handset with the polar heart rate belt coming with it. So you have a wireless sensor coming with your mobile phone. It's a good example. And finally, building automation, which is someday going to be the most ubiquitous part of this technology, will be this technology deployed in all kinds of buildings. And what's happening is that now, with the advent of this new 6LoWPAN technology, is that all these applications are becoming Internet connected. And I don't always mean Internet with the big I. Sometimes it's Internet with a small I. Sometimes these are closed IP networks. But they're all being connected with Internet technology. And then we really start to see the potential for seeing trillions of nodes connected to the Internet. So this is a huge engineering challenge. It's a huge social challenge. We don't know how to maintain or even regulate such a network that's that large. It's a huge challenge for the scalability of these networks and for the security of these applications as well. So it's a huge opportunity for us in industry, for you in research, in the research world, and it's also a huge challenge. There's a lot of problems to be solved. So it's an interesting time to be involved with this. So this is the big vision. And 10 years ago, this was only a vision. The interesting thing is today, this is happening. Just in the last months, the entire US smart metering industry has started to standardize on this IPv6 technology. So we see very interesting trends of everybody standardizing on IP technology. In practice, the way I like to define it is that when we start combining IPv6 technology with low power radios, so all kinds of low power wireless links, this is what in the book we call the wireless embedded internet. This isn't a term that's existed before. We made up this term to try to explain this new domain. It's about the Internet of Things, but it's not just about any Internet of Things stuff connected. It's about small wireless low power devices. And 6LoWPAN, so the technology we wrote about here, is what makes this possible. So this is a new standard that makes it possible to use IPv6 in these really tiny devices and over very low power wireless networks. So what are some benefits of this? I mean, why do we do this? Why do we even try to use the internet in these applications? In the old days, everybody just used to say that, oh, we don't need internet there. We just use proprietary technologies. But there's some very good reasons why we're doing this. One of them is long-lived standards. A lot of these proprietary techniques don't stick around for more than a few years at a time. We had Zigbee 2003, we had Zigbee 2005, we had Zigbee 2007, and then we had Zigbee Pro 2008. And guess what came now? Zigbee IPv6. That's the next thing. So now they threw away the whole garbage because it just didn't stay stable for long enough. So we see this trend happening all over the place, that people need standards that will stick around for 20 years, not for 2 or 3. This is a good reason. Easy learning curve, everybody knows the internet. We want this stuff to integrate with the internet because that's where the users are. All the customers want to use this stuff through the web, all of these services that are enabled by this. So why not connect it directly to the internet? We know about maintainability, we know about scalability, and we know about the importance of making data end-to-end because we don't want the infrastructure in between to get involved because that hurts scalability, it hurts innovation. So there's a lot of very good reasons for applying IP technology here, and this is the reason why so many people are interested in the new technology. So I have a little history of what's been happening in the industry, just people put in perspective what the newest developments in this are. In the old days, so 1980s, what was sensor networking? We talk about sensor networking sometimes when we talk about this technology. Cables. Cables is great for sensor networking. You plug it in, it works. The only problem you have is it's expensive, and if you cut the cable, it's really broken. The other problem is that it's very inflexible, so we don't have any kind of real scalability with that. You can't just cable up everything. In the 90s to late 90s, we started to have proprietary radios and networks. If anybody was in industry in those days, Antti here was, it was a disaster. You tried to find a wireless technology for your application, you'd have to go through like 10 to 20 different ones. Everybody was the best and had their own special. Z-Wave is one good example of this. So vendor lock-in, no real scalability or flexibility, so we're really stuck. In the early 2000s, we had the IEEE 802.15.4 standard, and we had something called Zigbee. This was a big breakthrough because the first time we had a wireless standard that we can use. It turns out that Zigbee wasn't the best solution either because, again, we had a lot of complex middleware, we had real problems with scalability, and we had problems with standardization. So things didn't stay standard for long enough. And what's happened now in the later part of the 2000s is that we've started to go towards internet technology. And one of the big breakthroughs we had, and this was the result of the research we've done here in the Oulu region, one of the big results of that was moving this embedded IP technology to standardization. And when you do that, that's when things really take off. So in 2007, we finished the first standard on embedded IP. And this is called 6LoWPAN. And that's what this is about. 6LoWPAN is a way to use IPv6 in very low power networks. The other result is that this was adopted by the entire industrial automation industry. So there's another standard called ISO 100, which builds on this, and I'll mention that quickly. And so now, almost the entire industry that wants to use either for normal machine-to-machine or for industrial uses has standards that they can apply. So now we've gotten to the situation where we have very open, long-lived standards, and we have pretty good grasp on scalability and reuse of the technology. So this is how things have happened over the past couple decades. Nowadays, there's a lot of standards bodies involved with this. To give you some perspective about what's happening in the industry, this looks like a little bit of a spider web, and it is. But everything at the center is in the IETF. So and this is where I'm strongly involved myself, and SensiNode as well, is in supporting IETF standards, because this is one of the most open standardization processes in the world. So this is where IPv6 is standardized, this is where 6LoWPAN is standardized, and this is where something we'll talk about a bit later, which is routing. A routing protocol is standardized. And we have a lot of different alliances around this. Something called the IP Smart Object Alliance, which is an industrial alliance promoting IP. We have Zigbee now using IPv6 technology. 15.4 is connected here. ISA is an industrial automation standardization body. ETSI is also standardizing M2M based on IPv6 technology. And of course, there's the Open Geospatial Consortium, which is also using web services and IP technology. So there's a whole web of standards now all pointing to IP technology in the middle. So it's a very interesting spider web happening in the industry right now. There's quite a broad range of applications that we can use this with as well. Nowadays in the industry, there's a few very special ones where the money is. And this is where you see most of the hype about. Some of those are, for example, building automation. This is a very important one where there's real business today. Another important one is advanced metering infrastructure, so energy. This is something where there's a lot of business going on. And asset management or logistics and these types of applications. This is also something very big right now in the sensor networking industry. But there's a lot of other applications coming as well that are going to be big things. If not right now, they're going to be big things in 5 years or even 10 years. So for example, personal sports and entertainment, already starting to take off with personal sensors and devices. Healthcare, something that in this region with the Vilho projects that we did with ESCO here was very cutting edge, because we were applying this technology to healthcare already years ago. And this is something that's coming all the time. We're seeing it coming. Environmental monitoring is going to be very important. Weather monitoring, security, and of course industrial automation is something that's becoming quite big as well. Now I have a few examples, a few from the Sensei project. This is one big EU project where we're involved with. And I used quite a few examples from Sensei in this book to try to illustrate where you can use 6LoWPAN. I also have a couple examples from the Oulu region that I'll explain too. So one very good one is facility management. So facility management is not just building automation. It's building automation, it's access control, it's energy monitoring, it's building management of how the building's used and utilized. It's meeting scheduling, it's all kinds of things. A very important one for this kind of IP technology, because we can integrate lots of different applications over the same network infrastructure. One important example I want to give, and this is one that we showcased in the book, is the use of 6LoWPAN in access control. And this is an important one because we did this together with an Oulu region company, so Idesco Oy. So Heikki in the back is coming from Idesco. And we showcase this in the book because this is an excellent example of applying 6LoWPAN technology in a building automation type application. So as you all know here, Idesco is a very well-known RFID manufacturer. And they have a product that you can look at in the web. This is called the Idesco Cardia system. So this happens to be actually one of the first, as far as I know, the first wireless RFID access control network where the backbone infrastructure is wireless. Of course, RFID is wireless. But all that stuff behind the RFID readers is a whole mess of cables. Well, no more with this. What they did here is they removed all those cables and put a 6LoWPAN network between the readers. And so you have, instead of all this wiring, you just have some readers, some door control units, and an access screen. And with that, you're able to build a small to medium-sized access control network. So the interesting thing was there were some pretty nice benefits from using 6LoWPAN. For example, a huge reduction in installation time and cost. So instead of having to wire everything up, you could actually just place these easily on the doors. Some flexibility for temporary installations, for retrofitting. And especially one interesting thing for the market was that you could start to apply RFID access control for very small offices. So there wasn't any more this price, this 20,000 euro price barrier to get this into a small office. You could simply install a simple wireless network. So very good example of using this technology. Here's an example of how such a setup would work. Simply some RFID readers here and there, an access unit. Also some outdoor units are possible. So wireless RFID. So if you want more information on this, you can actually get this from the web, or in the book as well, we have an analysis of this case. Industrial automation is another important one, and this is one that we also showcase in the book. We have a whole section on the ISO 100 standard. I just explain a little bit what ISO 100 is, because this is going to be a very big thing in the industry in the future. ISA is something that probably none of you here know about. I know a couple of you have actually looked at this, so you know, but before I started getting involved with this standardization body, I'd never heard of it before. So it's a little bit of a specialized one. So ISA is one that specializes in the automation industry. It's a little bit American-centric, but they specialize in automation and process control. And they're actually a standardization body. And what they decided to do about 3 years ago was to get rid of all these proprietary automation systems. So Honeywell had their own, Honeywell One, Emerson had their own, every single company had their own automation system. And instead of doing that, they decided to make one ISO 100 standard called ISO 100 to bring those together. And what this does is it uses an 802.15.4 radio. It adds some frequency hopping for reliability. It applies 6LoWPAN networking on top of that, so IPv6. And then it's able to build up an entire system. So it's not just a network standard, it's a system standard. So it defines everything from the gateways, security management, every single piece of the entire industrial automation system. This means that it's an 800-page standard. So I don't recommend you to go dive into that if you're wary of getting your head full. But it's really 800 pages. So the downside of making a system standard is it gets very complex. The interesting thing is that this has already been released now in 2009. The first version's out there, and the first products already start to be available. So this is a very interesting thing for industrial automation. Architecture looks something like this. And we'll see later this is very similar to other IPv6 networks. So they're actually separating the plant network from the automation system backbone network. These are actually can be two IP networks, and this can be a router, but they separate those. And then they use backbone routers to create these infrastructure-based automation networks. A little bit about the internet before we talk about 6LoWPAN. I think it's important to understand how the internet infrastructure works. So one important thing to understand about the internet is there is no internet. It's maybe the way I like to explain it, that the internet as a single entity doesn't really exist. There is no one internet. All the internet is millions of small, very small networks which are interconnected together. And that's the importance of what the internet protocol does. The internet protocol really just integrates a whole bunch of different link networks together and make it interconnectable and globally usable. And the internet's going to do the same thing for 6LoWPAN technology. Now I'll explain how that works. So instead of having networks with proprietary technology or specialized technology in every network, we make that a virtual network. We go one layer up to the network layer. We give it its own addressing space. And we make that all integrate with the same infrastructure. There's no real centralized control of this network. That's the other interesting thing. So the only centralized control there is a naming authority. So the only centralized control on the internet is naming. So who gives out domain names, who gives out the identifiers of protocols, and that's it. Today there starts to be some governance things. The only place where there's really documentation about how the internet should be used is from the IETF. And those are just protocol standards, so technical specs. So the internet really is quite a free-grown network. And this tells you a little bit about what's going to happen when we connect trillions of networks here. It's going to grow organically. And this is why I'm not too worried about connecting trillions of networks. It's because the way the internet's grown so far has been very organic. When there's a problem, smart people have tried to figure out a solution for it as the problem comes. And hopefully a little bit ahead of time so the problem doesn't kill the whole thing. I think we're going to have to use that same kind of thinking to solve the trillion node problem as well. What the internet is in practice is just about anything that connects together with the IP protocol. We think of IP as the narrow waist. So IP is the thing that everything goes through. It makes all these different link layer technologies look like the same network. And it makes all these different transport and application protocols work together over the same narrow waist. So this is sometimes called the hourglass. Unfortunately, these days, this starts to be the hourglass waist, but that's a different discussion. But that's because of security firewalls and things like that. And the internet architecture looks like this. So when we do routing in the internet, we actually do routing hop by hop through the internet layer. And that's the important thing about the internet protocol, is that all the routing in the internet protocol goes through the internet layer. The application protocols above that don't get involved. So we have what's known as peering relationships between above protocols, and that's from end to end. So that's a really important concept of the internet, is that we separate the networking from the transport and application peering. So the relationship between the transport and application protocol. And this lets us make independent processes here on this device talk with another process on another device on the other side of the internet, and keep that relationship separate from all the other millions of processes that are talking to each other. So we really decouple these things apart. And this is part of the reason why the internet has scaled the way it was, is because of this separation between routing here, transport, which controls our flows and makes the internet stable, and the actual application processes. Now, up till now, we've been using, well, actually since 1979, we've been using the same IP protocol, IP version 4. Now it's about time for an upgrade. We're running out of addressing space. We're running out of capacity in routers because of the difficulty of routing. So in the late 90s, the IETF started developing the next generation of internet technology, and this is called IPv6. And IPv6 is really a complete redesign in addressing. It's not such a redesign in IP. It does basically the same thing, but it's a redesign in how we do addressing. So instead of using 32 bits to address devices, we went all the way up to 128 bits, and we added a lot of hierarchy. And this hierarchy allows us to organize networks in a much nicer way, make routing more scalable, and it allows us to do nice things like auto-configuration. And the benefit of that, or the side effect that nobody thought about back then, is that this is actually what allows us to do 6LoWPAN as well. So the side benefit of having this hierarchy is that we can actually compress this stuff very nicely. And that's what I'll show when we go to the overview of 6LoWPAN. So many of you might say, but wait a second, IPv6 is not here yet, I'm not using IPv6. It's partly true, but in reality, there is actually a global IPv6 infrastructure already deployed. It's out there and it's working. I use it every day. And very slowly but surely, PCs have been converting to IPv6. All of your PCs have IPv6 enabled, or they're capable. A lot of governments are starting to require IPv6. For example, the Olympics in Beijing were totally IPv6 based. Every single PC, every single embedded device, the entire Olympics was IPv6 based. It was a very good example of the Chinese applying IPv6. And the reason is simply because they're out of addressing space. Totally out. So the Chinese have to do IPv6. So it's they have an interesting motivation to do it. We saw some interesting statistics recently that the annual growth rate in IPv6 is something on the range of over 1,000%. We saw 1,400 to something between 1,000 and 2,000. So it's growing very fast. The nice thing about IPv6 for embedded application is that there is no existing infrastructure for these embedded applications. So for us, there is no transition. There's no problem starting with IPv6. We have kind of a clean slate, you could say. So we have a real interesting opportunity to deploy IPv6 the first time and do it right. And that's what we saw happening as well. This is what the header looks like. So IPv4 was a bit of a mess. Lots of small header features, and this was extensible as well. IPv6 is much cleaner. It's a heck of a lot bigger, but it's much cleaner. It's a very simple header. And we have extension headers, which are much easier to parse. The addressing also looks a little bit funny. So instead of addressing things in this style you're used to, the addresses in IPv6 look like this. They're hexadecimal. They're not meant to be user-friendly. They're meant to be very user-unfriendly. You shouldn't care about IPv6 addresses. You should care about www.google.com. That's what you care about. And that doesn't change. The domain name works with both the same way. The interesting thing about this is that this actually is in hierarchical chunks. So the first part has to do with the network. The second part has to do with the network interface. And this is an interesting feature that I'll explain why that works like that. IPv6 itself is only a format. IPv6 actually doesn't have much of any smarts. It doesn't do anything. It's just a way to represent this stuff, and routers in between do something with it. The actual brains in IPv6 is something called neighbor discovery. And neighbor discovery is the protocol which defines how computers and different equipment on the same local network, so the same Ethernet wire, how they talk to each other. And that's a very important feature because that allows these networks to actually work auto-configured. So it lets you find neighbors, it lets you find routers, it lets you resolve addresses, lots of other features. So neighbor discovery is very important. And it looks something like this. So when your PC comes on a network, it sends a router solicitation, say, hey, is there any routers out there? Gets back a router advertisement. And then after that, it uses what's called neighbor solicitations and advertisements to do everything else. It's a totally distributed algorithm. So every device is responsible for taking care of itself on the network. As we'll see later, that has some bad implications. So it assumes that all devices are on all the time. It assumes they're all powered, so it doesn't matter how much energy they use. So it assumes some things about devices. It also assumes that we have Ethernet, which is not always the case. So what actually is 6LoWPAN, other than being a very bad acronym? I'm not responsible for this acronym, by the way. We had a much sexier name in the CWC when we were working on this, and it was called Nano IP. Nano IP was a much better name. This should have been called Nano IP, but we wrote a draft back then, and nobody listened. It took a few years to get it in here. So these guys came up with 6LoWPAN.
Actually, we used it.
Yeah, Nano IP was actually used. And where was Nano IP used? Oh, really?
Yeah.
The old Nano IP?
Yes.
Cool. It's good somebody's still using it.
We have to find some protocol, and we thought that this is as good.
Yeah, Nano IP is still a good protocol. So Nano IP was what we called this back then. Yeah, that was a good. I didn't know that. So this is defined by IETF standards. So we have a standard. IETF standards are known by these funny numbers, but you can actually go look these up for free on www.ietf.org. So 4919 and 4944. These days we're in 2009. The first standards were done in 2007, so we're already on generation 2. So we've already made some improvements. And these are known as these. So we have an improvement in header compression, neighbor discovery, and routing. So 3 new standards that are coming out. And what this does in practice is 6LoWPAN gives us stateless header compression. So it allows us to compress IPv6 down statelessly. So that means we don't have to discuss beforehand to agree on what we're compressing. We simply compress and everybody understands it. So that's called stateless header compression. We're able to use standard socket APIs, standard application protocols, things like that because this is IP. It's still IPv6 actually. It's not incompatible. And one of the most important features of this is that we tried to reduce the amount of code you needed and the amount of memory you needed. So this is supposed to be friendly for these very small devices like this little radio module, which we use quite often for lots of different purposes. So this is only about the size of my thumbnail. So we can use IPv6 and run internet protocols there. And finally, one of the nicest things is that this enables direct internet integration. So no gateways, no fancy manipulations of things, but real IPv6 routing between sensor networks and the internet. The protocol stack looks almost identical. The only difference is that instead of just having IPv6 here, we have IPv6 with what we call the LoWPAN feature. You could show this as another little layer below IPv6, but I like to show it as the same because this is actually how you implement this in practice in an embedded device. So it's IPv6 with this LoWPAN feature. The other thing you don't see here is TCP. And the reason for that is TCP is not all that useful in low-power wireless networks. It doesn't deal with wireless loss, packet error rates very well. So TCP is not very efficient. So you tend to see UDP used here in addition to ICMP for transports. The other thing I don't show here is HTTP because that turns out not to be very useful over very low power, low bandwidth networks. I'll explain a little bit more about that. A couple of features I want to mention, other than supporting auto configuration and all those important things addressing, this also has support for fragmentation. So if for some reason we do need to transmit a much larger packet, say 500 bytes or 1,000 bytes, we are able to do that. It's not very efficient, but we are able. So that's an important feature for backward compatibility with the rest of the internet. So what does the 6LoWPAN architecture look like? So if we think about this as being the internet, this as being the University of Oulu network, so the university network here with a backbone Ethernet switched infrastructure. We can think of 6LoWPAN as being little islands of stub networks connected to this internet or to local networks. So 6LoWPAN networks are really, if we think about the internet being made up of millions of small network domains, the Internet of Things will be made up of billions of very, very small network domains, which are connected to those small network domains. So 6LoWPAN networks are not transit networks. We don't use 6LoWPAN networks to connect your laptop here, because the bandwidth is totally insufficient and a lot of other reasons. But instead, this is the end of the internet. We thought this was the end of the internet, but it actually wasn't. This is the end of the internet. So 6LoWPAN lets us connect these very low power networks right at the end. We can connect them through different kinds of what we call edge routers. We can make very big infrastructures, kind of like Wi-Fi. We can make a Wi-Fi type of infrastructure with the 6LoWPAN technology. We can connect them directly through one router to the internet, and we can even make ad hoc LoWPANs. So we have the capability to make these standalone ad hoc networks as well.
Can you make mobile networks?
Yes, and I have a whole 50 slides on that.
Can we go quick through?
This is why you have the book. There, section 4. Yes, we can do mobility. Now, this is actually something interesting about IPv6, is that IPv6 does have some features for mobility, and we do make use of those. So you can have mobile networks. In fact, mobile nodes and networks. We'll talk about the difference. I have a little example of addressing, too, what this might look like. For those of you that know a little bit about IPv6, what happens in an IP6LoWPAN network is that we compress this thing down in such a way that the entire 6LoWPAN network, so this is the 6LoWPAN network, it's connected through a router to the internet. It shares the same network prefix. So in IPv6 we have network prefixes. Here it's 2001 300A, 1. This network prefix is hierarchical, so this is actually related to 2001 3000A, which is above it. This is just assigned a 1 to differentiate between that. And all the nodes in this network, so all the 6LoWPAN nodes in the same LoWPAN, they share that prefix. So that prefix is what's called the well-known prefix. It's the LoWPAN prefix. So all the nodes in the network actually only have their MAC address, and that MAC address might be very short, 1, 2, 3, 4, 5, 6 even, if you hand assign them. So the way 6LoWPAN works, the simple way to understand it is because we know this, because we know everything we need to know about this little tiny embedded network, we can compress all that away. So everything we know about the network, we compress away at the edge. So we end up with very compressed networking inside that network. But it's lossless. We don't lose any information about the IPv6 network. We get that back when you exit the network. This is a very simple example of how 6LoWPAN works. Of course, the foreword for the book, we're very happy. We got Vint Cerf to write the foreword for the book. We know Vint from standardization. And Vint had a very good saying in the foreword of this book. He said that 6LoWPAN is the answer to the future, but the devil really is in the details. So I say it's very simple here, but when you start looking there, of course, you always have some details to work out. So the fine details of this can be a little bit complex, but the result is very nice. This is what the headers look like, and this gives you a very good example about why we do this in the first place. So the thing about IPv6 is that although it's nice for the future of the internet, it's very big. So in the 802.15.4 standard, so Zigbee radio standard, the frame sizes, so the size of one radio frame, it's only 127 bytes. After the MAC headers, we have something like 100 bytes to work with. If you would use IPv6 and UDP in that, we end up with something like 50 bytes of payload. What do you do with 50 bytes of payload? Not much. In theory, it could work, but you're not going to end up with much to work with. So what 6LoWPAN does is it compresses all of this, so this part here, down to that. So in the best case, we can get all that down to 6 bytes. This is in the best case. In the worst case, it might be 12 bytes. So this is the interesting thing about the technology. We compress down to from 48 to 6 bytes. This leaves us with what we feel is pretty sufficient. From industry, we know this already. We can use this. And in sensor networking, we've already found that 100 bytes starts to be a reasonable amount of space to work with for these applications. This is the same picture in IETF style. So this is the packet header style that we use. Note this is ASCII art. IETF still uses ASCII art. If I would be a purist, I should have written that architecture diagram in ASCII art, but I'm not that much of a purist. That's just painful. So here we have IPv6. It ends here. Then we have UDP. And then after that starts the payload. This is what it looks like normally. After 6LoWPAN, it looks like this. So basically, IPv6 doesn't exist. We actually compress most of IPv6 away, in the best case. And UDP is only 3 bytes long. And then immediately we start with the payload. The way 6LoWPAN works, and you'll see that from the book or from the full slide set, is that it uses bitmaps. So it uses a bitmap for telling which things are compressed. So it's a flexible compression. You can actually leave some parts compressed, some parts uncompressed. This is quite handy because sometimes for different kinds of networking, we need to leave different parts of the packet uncompressed. But what about the link layer? What kind of link layers can we use with this technology? And I think this is very important because in the beginning, and this is the link layer, by the way, so the medium access control above your physical layer and just below IP, that's the link. In the early days of 6LoWPAN, 6LoWPAN was thought to be applied only to 802.15.4. So 15.4 is what's called the Zigbee radio sometimes. That was the original idea. But what we found out from working with it for a few years is that you can actually apply this technology to just about any type of low-power RF link. So in the later years, we've now made this more general. So now we can use this with narrowband RF, all kinds of funky military radios, any kind of radio you can think about that has some features. And those features, for example, are some framing, some kind of addressing, unless it's point-to-point. Point-to-point doesn't need an address, but any kind of multiple access needs addressing. A little bit of air checking, some kind of length, not too much to ask for, and some kind of broadcast or unicast service. So if you have those things, and around 40, 50, 60 bytes of frame size, you can use this technology. So I see the wireless researcher guys going through the head, oh, I have lots of those radios. We know lots of those kinds of radios. There's tons and tons. So we made this very generic these days. Now, one of the important things I mentioned earlier was about neighbor discovery. And the reason I explained a little bit about how IPv6 neighbor discovery works is because it happens to be that that doesn't work very well in these networks. So after a few years of using this technology, we found that there's much better ways to deal with setting up networks and maintaining them. So we have a new standard that's just about to be completed. And this is called 6LoWPAN neighbor discovery. And what 6LoWPAN neighbor discovery does is it changes the way that neighbors on LoWPAN networks talk together. So on IPv6 links, Ethernet for example, we assume that everybody talks to everybody. It's distributed. Everybody's on, everybody's powered. If you have anything to say, you just shout, and everybody else hears you and answers. But in a LoWPAN network, we can't assume that. We have sleeping embedded devices. We have very, I don't say bad, but yeah, lousy. In fact, we have a working group called routing over lossy links, but we call it routing over lousy links because they're lousy. The packet error rates are very high. The connectivity is intermittent. It's a very difficult environment. So you can't assume much about it. So the things we did is we made all the traffic node initiated. So we made it that it's actually the wireless node which controls its traffic. We made a node registration mechanism. So instead of everybody shouting to everybody, we made it that the wireless device registers with its router. So it controls when it wants to work, when it wants to wake up, when it's time to register. And then doing that, we enabled all this stuff that you need to do to make these networks work. So neighbor unreachability detection, duplicate address detection, as well as enabling address resolution. So we basically bundled all these things into a simple registration message. So this is how neighbor discovery for this type of network works. This is currently in progress. I'm actually the editor of this document. So if anybody has questions about that or comments, straight to me, my email. I'd appreciate it. This is how this looks. This looks in practice. So this looks the same. This is now a multi-hop network. So the other interesting thing about 6LoWPAN is that we no longer have only an Ethernet network where everybody is connected. We have a wireless link. And wireless links can be routable. So what happens in a 6LoWPAN is we have multiple IP hops inside this mesh network. So we can have this RSRA like normal, but now instead of doing NSNA, we do this node registration. And so this host will register with its router, gets a confirmation back. This router has already registered with the edge router. And in some cases, to enable network-wide activities, will actually register with the edge router as well. So everybody registers with their router. Registration might sound a little bit heavy, but the way we do it is actually quite light. This is a soft binding, and it can be very long-lived. So we're not talking about registering every 30 milliseconds. We're talking about registering every day, or even every week. We have it up to a week. So this can be a very slow registration. In some embedded applications, that's quite useful. We have nodes that sleep for several days at a time. In the current internet model, they would have to wake up all the time to check if anybody's talking to them. But here they can actually sleep for days at a time. After you've done that, you can have normal data flows going through the network. Security is another very interesting and important topic. So especially when we deal with not only embedded networks, but wireless embedded networks, security becomes even more interesting because we have vulnerability because wireless radios can be very easily overheard. So this is one of the big difficulties of wireless. It's very easy to conceal your network. Everybody can hear that who's in range. The other problem is we're dealing with embedded devices. And the problem with these embedded devices is that they have very limited amounts of processing power, limited amounts of power, and they don't have human users. So you can't install a Windows security update on your little temperature sensor. It's not that easy to do that. And then to fix it when the thing breaks. I mean, this thing really have to be secure autonomously, so with no administration. And that's a really big challenge. It's not easy to do. I won't go more into the details of this. We have a really good section written by Karsten in the book And he's actually one of the few people that's able to explain security in a simple way, because I'm not a security guy. It always confuses me as well. But he actually writes it in a simple way, so I recommend that. I just point out a few major areas where we are doing security work with this technology. One is at the link layer. So this 15.4 standard actually builds encryption into the link layer. So that means that when you put an encryption key there, it automatically will encrypt all the data that's going across the link. So this helps a little bit with this. This prevents some of the overhearing, because if you don't know the encryption key, you're not able to understand what's being said. You can hear that something's being sent. You don't know what. We have layer 3 mechanisms. Layer 3 mechanisms are important in addition to this, because layer 2 only helps you hop by hop. As soon as you go through a router, you're vulnerable. So every hop, when you're at a router, it's unencrypted, goes through the IP stack, encrypted again. So if somebody gets into your router, all your data is understandable. So IP encryption allows you to do this end-to-end, and that's done with something called IPsec. And it turns out that a very minimal version of IPsec is applicable here. It still needs some work, but it can be usable. The other thing we do sometimes is we do application security. Because in some cases, even IP security is not enough, because you might have a web service blob somewhere in the middle of this thing. And if you have IP going to web services, again, you're vulnerable in the middle. So what application security does is that does security end-to-end. We can even secure the application data blob itself. So we can do object security, where not even the person that doesn't have the rights to that data can't open it until it gets to the right place. So different combinations of these security, we can actually secure these networks even for very sensitive applications. I recommend this. For anybody who's looking at security interested, I recommend this RFC 3552, which talks about the internet security model. So it talks about what you have to think about in internet security. I'll skip over these. I explained these already a little bit. I'll put these slides on the web as well. We're going to have actually this whole video will be on the web. So anybody that has a friend who wants to see this, I put this on the book site so you can actually see this presentation as well. So you can go back. Now we'll talk to the part that Anti's excited about, so mobility. I'm a bit scared. What do you want to do here? You want to put this on your motorcycle and drive through Oulu, or? Okay. So what is mobility? This is an example of an asset management application we looked at in the Sensei project, so in a warehouse. Mobility in practice, the way I like to define mobility is any time in a network, so network mobility, when your point of attachment changes, so your topology. So anytime we have a change of network topology, this is what I call network mobility. And this is the general understanding of what network mobility is. It turns out there's quite a few different types of network mobility. There's what I like to call micromobility. So micromobility is mobility within the same IP domain. So this means that you're moving within the same Wi-Fi infrastructure. This is a good example of micromobility. Or you're moving in the same LoWPAN. So in our case, the 6LoWPAN, it's moving in this same LoWPAN infrastructure, which has the same prefix, so the same IPv6 prefix. This is micromobility. And this has a lot to do with the routing. So when we start talking about routing, we're talking about this case usually. The other case is what I call macromobility. And macromobility is when you switch from one IP network to another. And this is a big difference, because what happens when you switch between IP domains is that your IP address changes. And we know what happens if you're on your laptop and your IP address changes all of a sudden. You're done for. You've got to reboot your browser, restart all of your stuff. Your TCP connection is just broke. It breaks most everything if you do that. So these are the two different types of mobility.
How about third case? You are a network. You have a device and nodes, and then you walk through the internet.
Anti's on the same, very much in the same line as me. So network mobility. So yes, this is a very special case, and in fact, it's a really important case for sensor networks because we have a lot of this. And this is where not only does a sensor node move, but the whole sensor network moves, or the whole 6LoWPAN. So the edge router and all the nodes associated with it, so connected with it, move. And the edge router's point of attachment changes. So think about this as a mobile phone and its sensors. This truck that we had back before, this little truck in the warehouse, that may have sensors on board that are wireless. That will be part of the same mobile network. And to deal with this, we need a little bit different features to be able to handle this. It actually turns out that this is a much easier problem to solve than the node mobility problem for 6LoWPAN. Because this guy happens to be usually a Linux, embedded Linux device. And we have lots of power, protocols, techniques there. These devices are little tiny 8-bit microcontrollers. They're a little bit harder to add features to, so we have to be careful there. So that's network mobility. Now, I didn't spend time in these slides talking about all the different ways we have to deal with mobility. I mentioned just a couple. One is called mobile IPv6. You can find those from the full slides that I'll post today on the website. So mobile IPv6 is a standard, one good solution for node mobility. But it doesn't help with network mobility. For network mobility, we have another standard from the IETF. It's called NeMo, network mobility. And NeMo allows you to do this. It allows you to do mobile IPv6 for this entire network. So to these guys, it looks like nothing's changed. They see the same IPv6 prefix all the time. This guy handles all the changes for them. So please look at the slides in the book for more mobility information. There's a lot of information there. Now, something really interesting for many researchers is routing. Routing is the favorite research subject for everybody because there's an endless amount of work to be done here. And the same thing is true today. There's a lot of work left to be done on routing as well. So routing in 6LoWPAN, we talk about IP routing. There are mesh routing techniques or link layer mesh techniques. You can use 6LoWPAN over there, but then you don't have to care about that routing. It's done under you. Here we talk about IP routing because this is what most of the industry is going towards, is IP routing. So routing means that we forward packets here within the 6LoWPAN network. We're also doing routing here, but we'll leave that out of scope for now. So we're doing routing inside this network. And what routing looks like in an IP network is that, like this. We actually, at every hop, we go up to the IPv6 layer, back down again, up to the IPv6 layer, back down again, and finally to the end destination, the destination IPv6 address, and then up. So IP routing always involves the IP layer. And IP routing always involves the routing tables. The interesting thing about IP is that IP doesn't do routing itself, or IP doesn't make routing decisions itself. So IPv6 is not a routing algorithm. So the interesting thing about the internet architecture is that IPv6 and routing algorithms are separated. So IPv6 is open to any routing algorithm. So every single network segment can decide what routing it wants to use inside that domain. So it's really domain-centric. That means that we have our own domain here, so we can choose what kind of routing we want to do here. And that can be different than what's done here. So the routing algorithm will maintain all these routing tables in the network. And based on those routing tables, we'll make routing decisions. There's a few interesting things about LoWPANs which make them a little bit different than other types of networks, or other types of IP routing. One is that we're doing routing on a single interface. So those of you who have done routing on a Linux box, what's different here? On a Linux box, you do routing between Ethernet 0 and Ethernet 1. And you do prefix-based routing. So you say, if this prefix comes, send it there. If this prefix comes, send it there. But in a 6LoWPAN, we have very simple wireless devices. So we only have one interface. So here we have to do what's called exact match routing. So we don't have prefixes to work with. We have exact match. So if you want to make a routing decision, you have to say that, the destination is this guy, so send it there. If the destination is this guy, he sends it there, etc. So you have to do an exact match on every address. we have a few different options for routing algorithms with IP. In some cases, some people tend to apply custom routing algorithms for their LoWPAN networks. This works really nicely in very, very specialized applications. I recommend people to use standards wherever they can. So there's really two different groups that you can get standards from. They're both in the IETF. One is called MAN-A. So MAN-A is a group that's been around for a long time. MAN-A does ad hoc networking protocols. And there are some of the protocols in MAN-A could be applied to 6LoWPAN if you're doing ad hoc networking. So we showed this network where there was no infrastructure. So anybody might talk to anybody. Ad hoc routing, it's very good with something like DIMO. DIMO is a pretty good algorithm for that. You have to modify it a bit, but it's applicable. But what we found in the industry is that there is no really good routing standard in the past for doing this type of routing in these types of industries we're working in. So building automation, energy, asset management, industrial automation. There's no good routing algorithms for that today. So a new IETF working group was formed about 1.5 years ago called ROLL, which we call, the insiders call, routing over lousy networks. It turns out to be low power and lossy networks, but they're also lousy. So these are developed specifically for these types of applications. So this is what everyone in the industry, so the commercial players are all applying this type of technology. And we're also very heavily involved with this standardization because we find that to be an important feature. So a MAN-A protocol works something like this. This is an example of an on-demand reactive protocol, which is distance vector based. So let's say that node 1 wants to talk to node 5. In order to do that, they need to flood the network with a routing request. So they'll send what's called a route request here. It's broadcasted again and again until finally the destination or somebody that knows about it hears that. They'll send a reply back, and by sending that reply, they build up routing state. So the routing table gets filled in. After that, they can use that route until the route gets times out or gets old, and then they have to start over all again. So very good for ad hoc applications, very bad for infrastructure-based applications. Don't say very bad, but not that efficient. This is, by the way, how Zigbee works. Zigbee uses an algorithm very close to this today. So the IETF ROLL working group, on the other hand, is looking at more infrastructure-based applications. So we actually did 4 different requirement specifications in the working group. So we looked specifically at home automation, building automation, industrial automation, and urban environments. Urban environments would be something very similar to the UbiLife project that's been going on here in Oulu. After analyzing all the existing protocols, it was decided that a new protocol is needed, that no work has been done before on a protocol quite like this. It's quite special. So a new protocol has been designed. It's actually in quite good shape now, and it's being implemented already today by quite many. And it's called RIPL, RPL. So the IETF ROLL RIPL protocol. And this is actually a proactive distance vector approach. Here's the draft if somebody wants to take a look. It's called proactive distance vector. And what does this proactive distance vector mean in practice? Well, this is what the architecture looks like. And what proactive means is that we actually build up state ahead of time. So proactive means we build up routing state before we need it, but we don't build up routing state about everything to everybody, because that's not what the data flows are. We build up routing state. These guys build up routing state about how to get here or here, and these guys build up routing state about how to get to these guys. So most of the data flows in these machine-to-machine applications are from nodes to internet or from internet to nodes. This is the most natural data flow that you have there. So it makes sense to actually optimize for that, and that's what's been done here. What distance vector means is that when this happens and you proactively build up state, the state is distributed in the nodes. So we don't have a centralized place where everything's calculated. Every node just has some information about what they need to know. The other important thing in here is that you have duplicate backup routes. So this isn't just one tree, you have multiple trees. So this guy could use this or this at any time. And in fact, in real time, it actually switches. So if this guy doesn't work, this will automatically back up to this route and use the other way out of the network. That's a very short tutorial for an 80-page specification. So it's quite long. So it's a little bit more complicated than that, but that's the general idea. The interesting thing about this is that this role algorithm is not only for 6LoWPAN. This has actually been defined also for Wi-Fi or any other low-power lossy network. So you can apply this to a Wi-Fi network as well. I'm very interested to see how this will compete with Wi-Fi mesh techniques, which have become the de facto on the market today. Will this be able to compete with link layer mesh for Wi-Fi? It'll be an interesting thing in the future. Cisco is very involved in this, so I'm guessing Cisco is going to start supporting this someday. The final thing we need to think about when we talk about routing is not only inside this network, but we need to think about how to route outside the network. And the most important thing that we need to consider when we do that is IPv4 interconnectivity, because we're dealing with IPv6 only networks. And that's the thing about 6LoWPANs, is that they are really IPv6 only. They don't even know what IPv4 is. That concept doesn't exist for them. So when we're interconnecting these with an IPv4 world, and we have to still live with IPv4 islands for quite a while, is quite interesting. The way it's done in practice, and I just have a little example here, is that we do tunneling. And so we actually tunnel over the IPv4 segments to reach the IPv6 part. So if you think about this is the IPv4 network, this is the IPv6 network. To get into this IPv6 network, we'll actually tunnel inside IPv4 to get to the IPv6 edge, and then it goes natively. So in this case, for example, everybody can tunnel to the IPv6 world, and we can talk between each other. That's how it works in practice. Nobody really does IPv4, IPv6 conversion these days. That's not really something that happens. Instead, you try to get into the IPv6 world directly by tunneling. And then you speak native IPv6. That's not a problem in the machine-to-machine world, because in machine-to-machine, we typically have a pretty small number of servers. In building automation, you may have a couple servers that you deal with. Same in energy. You have a few servers you might deal with. So it's pretty easy to enable those servers to be IPv6 ready, and then enable your sensors because they're already IPv6. Tunneling is standard. These are standard techniques. So you just tunnel. Let's say this is the server. Even if that's IPv4, you just tunnel to it. You can even tunnel directly to the server, and the server runs a tunnel broker. So these are problems that have been solved in IT for a long time, and we have techniques to solve them also for this application. So this isn't something that worries me very much. It's pretty much a done deal. Okay. So the final thing I want to talk about is application protocols. And then at the end, we have a demo, which has been very graciously set up for us by the UB-Life researchers from media team. So at the end of the presentation, we have a pretty cool demo where we get to control my house automation system remotely. Let's see what my wife thinks about that when we turn on and off everything. No, we're going to turn on that light, actually. So one important thing to understand about the internet model at the application layer, I mentioned this really briefly. We talked about the internet architecture, this peering, is to understand that the internet architecture, a very important part of it is the socket API concept, or internet socket concept. And the reason why this is important is that internet applications don't dominate the IP stack. So there's no such thing that we have, HTTP is the only application that can use the IP stack at one time, and then it has to wait if FTP is using the IP stack before it gets its turn. So everything's multiplexed, and this is what sockets actually enable us to do. So the internet socket layer, some people call it a layer, some people call it an API, it allows us to multiplex multiple application processes. And this is the important difference. It's not about the application layer in internet protocol development. It's about the application process. So it's actually an application process which gets a socket. So this one gets a socket, and it opens up that socket and communicates with another application process. So it's application processes that are connected end-to-end over the internet, not the application layer and not the application protocol. It's the process. This is an important thing to remember when thinking about these applications. In 6LoWPAN, we use very much the same model. The socket API is a little bit funky. It's minimal. It's embedded. It's in whatever language it is, but it's the same concept. It's a socket concept. Application protocols are pretty interesting also from the challenges we have in 6LoWPAN. There's a lot of benefits, but there's also some challenges from dealing with these very embedded networks. So these are a few things we pointed out. Some of these we talked about already earlier. There's some new ones as well. For example, we need to deal with firewalling. So the firewall problem doesn't go away when we deal with these 6LoWPAN networks. In fact, it gets even stricter because we don't have any network administrators for your little nodes. You have to protect them at the edge of the networks. So firewall is very important. We have these frame size and bandwidth limitations. So just applying XML, SOAP, HTTP, TCP over this network is probably not a very smart thing to do. You'll kill it immediately with the bandwidth. So this we have to think about. How do we deal with that? Multicast, it's expensive. So if you have an application which just multicasts everything and floods the network, you have to think about that. That might not be the best idea. How do you identify a node? And this is something we spend a lot of time in the book talking about, is how do you identify nodes? IP address might not be the smartest thing to use if that might change because of mobility. So do you use some kind of unique identifier? What about mobility? What does that do to your application? What about sleep cycles? How do sleep cycles affect your application? It's pretty interesting when you have nodes which wake up once a week. How do you talk with a node that wakes up once a week?
Do the routers catch the traffic flow?
Maybe, but that's not something that IP routers usually do. They don't usually buffer a packet for a week. It's a pretty funky router that does that. You'd have to really design that especially for that. So I think that kind of breaks the internet architecture a little bit. You'd have to do it at the application layer in order to buffer that. What some people do, what we do a lot in our commercial applications, is we make this node initiated. So we give control to the node. The server's there. When the node wakes up, it says, hey, here I am. Here's my data. Do you have anything to say? And it listens for a short time. Then it goes back to sleep. This might be one approach to doing that. Or you might have a proxy here in between, so an application proxy, and that does buffering. That's somewhere where buffering is legal for a week. It might buffer for the node.
How about radios interrupting the device?
Lossy links. That's what it looks like, lossy links. Or mobility. So if the link is so bad that you can't use it anymore, you change it. So a lot of interesting problems. Most of them solvable, but you have to consider these when making applications. The other interesting thing about these applications is that there are huge numbers of application protocols. Transports, we have quite a few. We have UDP, we have TCP, so the numbers aren't that large. But application protocols are very wide and varied. This picture really tries to point out some of the application protocols that we can already use today over these 6LoWPAN networks. So these ones in bold. We have things like SNMP, which is more or less usable, some modifications. SLP is a service discovery protocol. RTP is a real-time protocol, already very useful over sensor networks. We have something that we use in industry, which is an embedded web service type of protocol. That's usable because it's designed for this type of constrained environment. And we have a few others. This is one from IBM, which is for telemetry. MQTT is used by WebSphere and Lotus for telemetry. They have a sensor network version that's already usable over this type of network. So there are some protocols that are very useful. The problematic thing is that a lot of the protocols that you depend on today aren't directly applicable. For example, TCP doesn't work all that well. It might work for some applications, but for most applications it's a bit of a problem. HTTP is a big problem. HTTP header overhead, and the real HTTP that you speak with a web server is pretty complex. HTTP that you minimize by yourself and cut all the other things out, that might work for some things, but that's not the real HTTP that web servers talk. They want to negotiate. They want to set up security. It gets pretty hairy, and it's big overhead. FTP is also not all that useful because of TCP. SIP is just as chatty as HTTP is. And when you start getting into the web service world, it gets even worse. With SOAP, for example, different types of markup languages get very, very big. So we have around 100 bytes, 70 bytes to work with. We might make a few frames work with a few hundred bytes, but that's about all we have to work with in these networks. So I just made a couple examples about how people solve these problems today. So if you make an application protocol for 6LoWPAN today, what might you do? So one thing you might do is make a custom protocol. This actually happens to be one of the most common ways to make protocols for these networks today. Not only 6LoWPAN, but even over full IP networks. If somebody has an embedded device application and they need a special protocol, they just make a UDP protocol. There's nothing illegal about it. That's how internet protocol design is meant to work. You need a protocol, you make it over UDP or TCP. So you can put your own binary data there. You can make it very compact and efficient, blah, blah, blah. It works end-to-end without a problem. You have to configure firewalls and things like that, but it's doable. So the advantage is that it's actually pretty efficient and you can integrate security, all those nice things. The disadvantage of this is that, well, you need a custom server application. You can't reuse HTTP or these things. You're going to need to have a pretty big learning curve for this because you're going to need to teach everybody how to use this. You're probably not going to be able to reuse it except in your own organization. And then you have a pretty big interoperability problem when you get into the marketplace. So this is a little bit of a problematic solution. Another solution is RTP for streaming. So I didn't show this here, but I have another slide on RTP in the full slide set. RTP is actually pretty interesting for streaming applications, even sensor streaming. But one of the most interesting ones, and this is one of our conclusions from the end of the book, was that the biggest conclusion was that there's a real lack of application protocols suitable for these applications, which developers want to use and end users. So I don't talk about lack of application protocols. I had a whole list there. But those aren't the ones that many application developers want to use. They want to use web services of different kinds. And regardless of what kind of web service you use today, all of them are pretty chatty and heavy and not really appropriate for this type of network. So that includes pure XML, REST, SOAP, you name it. All of them are pretty heavy stuff for what the capabilities of the devices and the networks. But it's such a powerful paradigm, and it's so widely deployed on the internet, especially for enterprise applications, that there is a very big push to use web services in these networks. So we see this as the next big frontier in 6LoWPAN, is to work on and enable web services for these networks. The advantage of this is that you can use well-known schemas, XML or RDF, so you can specify your information. You can define formal message sequences using RPC, which web servers are already doing today. You have internet-wide support. You have no learning curve because people already know this. There's a lot of very nice advantages of this. Disadvantages, the inefficiency and complexity. And so what we're doing today, and the solution for this, is embedded web services. So this is something we've been doing for a longer time commercially, but this is also something we're working on with standardization today to really make part of the internet. So there's a new working group effort called 6LoWPAN. 6LoWPAN is an interest group in the IETF. You can look at that here, 6LoWPAN.net. And there's a new working group starting right now in Hiroshima, Japan. Last month, we basically kicked off this new working group. And this new working group has the task. It's actually called Constrained RESTful Environments, CORE. RESTful refers to the REST web service architecture, which is how the web works. The web is based on a REST architecture. So this working group has the task of making embedded web services. So this is a very interesting thing. If this succeeds, this is really going to change the way the Internet of Things works, because it means we'll have web services which are really efficient for these networks. The other things it means is that we'll be able to tie those web services, so this embedded web services in with the rest of the HTTP internet. And this is one of the main goals of this working group, is to not to make something totally proprietary or specialized which doesn't work with the rest of the internet. It's to make something that's so easy to convert to HTTP REST that it's just transparent. So these sensor networks will look like they're part of the rest of the web directly. So I encourage people to take a look at that. We discussed that a little bit in the book as well, and in the rest of the slides there's more information on this. That was to name a few application protocols. There's a whole bunch more, and I bet you there's some more that you know about that you could use over this. The nice thing about 6LoWPAN is it's IP, so you can use whatever application protocol you want. It's a clean layered architecture. So one good one to mention is device profile web services. This is something that's with compression and some optimization. This is very interesting. Another one is specialized application protocols for different industries. So in building automation, we use BACnet. It's very common. OBIX is quite interesting. And in the energy industry, we use things like ANSI C12 in the US and DLMS in Europe. There's a new standardization effort called Smart Energy 2.0 as well, which is looking at developing a energy solution over IPv6. So this kind of is the next generation of these things. These are pretty old-fashioned metering protocols. So a lot of things happening in application protocols today. Good. That's it.